Here at the Johnson Space Center, we specialize in preparing astronauts for the complexities, dangers, and challenges that human spaceflight presents. A team of engineers and scientists here have been using the assessments of physiology and cognition in hybrid reality environments, or APACHE Lab, to study how VR training can better prepare our astronauts for future EVAs, or spacewalks, on the lunar and eventually Martian surface.
There certainly are dangers on the lunar surface, but there are dangers on the space station. So when we go outside the space station and we do a spacewalk, at any minute your suit could malfunction. It could be your suit or your buddy's suit. So that could be anything from, your buddy has a seizure and they're not conscious, to you have a suit malfunction and you've got higher CO2 levels and they're not mentally functioning well, or they have a hole in their suit and they're on 30 minutes of oxygen and you need to get back to the airlock before those 30 minutes expire. So we practice this. In the VR lab, we practice it underwater in the NBL. It's one of the driving things that we actually make sure that the astronauts can do this successfully before they are signed off to go on a space mission.
As we move to the Artemis missions, they're going to look a lot different. We're going to have an unprecedented number of extravehicular activities, and not only in number, but in length. So we're going to be asking astronauts to do a spacewalk day after day after day. And so what we really need to understand is the psychological and physical demands of doing that.
So we developed VR immersive capabilities to kind of augment the training we do in mock-ups and in physical trainers. For instance, the NBL, the Neutral Buoyancy Lab, astronauts are full suited, they're in the water, they have mock-ups, but they don't have the visual cues, right? So virtual reality is perfect for that because you can create, a space environment with all the correct models and the correct lighting conditions. You're orbiting the Earth every hour and a half, so 45 minutes light, 45 minutes in darkness. You can simulate everything down to the, millimeter of accuracy in a virtual environment. So astronauts can train for spacewalks where they pick up their tools, how do they do their communications back with the ground and the cupola, and so immersive environment's important for that.
To really help our crew and to help our flight controllers on the ground, we're trying to build predictive models. So what the crew might be after they've gone 3 hours into the spacewalk, 4 hours into the spacewalk, how fatigued are they? And to get these kind of predictive models, you need a lot of data. And we can get a lot of that data in our VR environment, which is not as easily obtained in the spacesuit environments, where it's a lot of overhead, a lot of personnel. It's really hard just to get a test up and running. With the VR environment, we can do 2-3 tests in a day and just get through a lot more subjects, a lot more data is collected, and it really helps kind of just build those performance models for our crew.
So there's a lot of ways to test EVA concepts and tools and procedures right now. And unfortunately, there's no one-stop shop for everything. There's limitations and implications within each of these testing environments or scenarios. So we look at something like the Neutral Buoyancy Lab, or NBL, for example. As we put people in these lunar offloaded scenarios and have them walk and do things, their motion is impacted by the water drag that they have to fight in the pool. So that becomes kind of a limitation from the physical workload perspective. When we do testing out in field-based environments, like Arizona, for example, there's been groups to go out there and do some different research and testing. We find that we don't have access to the actual pressurized spacesuit, but we have the realistic terrain and environment where we can do navigation, we can do realistic geology. You just lose the physical burden of the spacesuit. And in any environment, again, looking at like Building 9 and being an Argos, for example, though you are in an actual spacesuit and pressurized, you're in a warehouse type environment, and there's a catwalk with tour people from the Space Center walking by and waving and having a good time. And so that can be distracting sometimes. For us, it's a lot of the same kinds of things here in our virtual reality environment. Some of the benefits are we can recreate tools and concepts and procedures and drop them right into the simulation, but we can actually put somebody on Mars so that they can do realistic navigation. They can get a feel for where they're actually at on the lunar surface or the Martian surface or wherever it may be, and really drive that immersion and cognitive workload, which we think is also a really important aspect for EVA. My primary role within this group, I lead the spacesuits and exploration operations team within the Human Physiology, Performance Protection, and Operations, or H3PO lab. A lot of the work that we do and are interested in is characterizing and understanding how an astronaut crew member is doing, faring, and performing while they conduct extravehicular activities or spacewalks.
So this building, Building 21, it's one of the newest buildings at JSC. It was built about 6 years ago. And when it was being designed and built, we were spread out across multiple buildings across JSC. And one of the goals, especially of this wing of the building, was to help us to integrate more closely. And so H3PO was the first lab to actually be an integrated lab. And so we're able to work with the other groups in the building, such as the Behavioral Health and Performance Lab, the Neurosciences Lab, and the Anthropometrics and Biomechanics facility. So these different groups that are in the building, we're able to work together to really solve these operationally relevant problems that we face with spaceflight, in particular EVA in this case.
We're in the APACHE space within the NASA Johnson Space Center, and we've built a VR environment to be able to look at cognitive and physical workloads that we would see during exploration operations. And so we can walk around on a treadmill within VR, which is what we call traversing, and then also work within a sandbox that allows us to do a little bit more of the geology tasks and maintenance tasks. And so it's a all-encompassing environment that we're developing within a virtual and hybrid reality environment.
So we find virtual reality to be really helpful in our EVA testing and research because, as you might imagine, getting actual access to a pressurized spacesuit and a partial gravity analog like the Neutral Buoyancy Lab or the Active Response Gravity Offload System, or ARGOS, it's really challenging. So for us, it's really important that we can simulate as many great aspects of EVA as we can in a rapid, controllable, and repeatable test environment. And that's really one of the beauties of virtual reality, is that not only can we recreate anything digitally and add the different tools and functions and widgets and heads-up displays and whatever else we might need, but we can actually drop somebody right there on the surface of the moon, of Mars, and see how they perform in the actual environment.
So that's one of the reasons we need a test bed like this. We're going to test a whole bunch of different scenarios. We're going to identify what we recommend to deal with each emergency situation. And then when we have a lunar crew who's assigned to go on this first lunar mission and land on the moon, we'll start training them, probably in these same environments, to go save themselves and save their buddy. And so this is both a test bed and it's a training resource. And yeah, I would say, anytime you get on top of a rocket or you are in your spacesuit and you open the hatch to the vacuum of space, there is definitely a level up in your head that says, why am I doing this and what decisions did I make in my life that led me to this point? But the point is, we're professionals, right? We are trained for this. We accept the risk. It's not just us that accepts the risk, all of NASA accepts the risk, and everybody at NASA takes that seriously. And this is why we do this testing, and this is why we do this training. And the amount of testing hours and training hours that go into a single mission is incredible, but that's the reason that we do that. We don't want to put anybody's life at risk unnecessarily. So we are definitely taking risk, but we are accepting the risk and we are mitigating that risk wherever we can. So you can think of this entire area actually as risk mitigation. This is making us safer. We know it's going to be dangerous, but this is bringing that danger level down because we're testing here and we're training here.
So today I'll be participating in the CO2 walkback study, as we call it. During EVA, one of the things that spacesuits must do is get rid of the carbon dioxide that humans are producing while they're breathing and doing work. In certain cases, we may be far away from the safe point or habitat on the lunar surface, and the spacesuit could fail in certain ways that would cause the CO2 to build up in the suit. And so the question that we're really trying to answer is, how much CO2 can build up before we start running into real issues. And so what we're doing in this study is trying to understand at what level of inspired carbon dioxide do we start to become unable to do that contingency walk back, to get back to safety and to protect our crew members. And so with the findings from this study will help inform requirements potentially for what the spacesuit will have to do and manage by way of CO2 to keep the crew members safe in those contingency scenarios. So one of the first things that we will be doing, safety first, we will be donning a safety harness strap. What we see is when we put people in virtual reality, sometimes they'll kind of lose the notion of where they're at in the physical world, and they can start to trip over themselves. And so we don't want anybody to trip and fall. So first thing, we've got a safety harness that we put on and walk through. Second thing that we are doing after that is donning a mock hard upper torso, or HUT as we call it. Spacesuits don't fit everyone perfectly. They are adjustable, and since we're doing a study that's looking at some of the respiratory physiology here, in some cases, certain crew members may not be able to take a full kind of complete breath in the spacesuit because of their size as well as the sizing of the spacesuit. And so we're trying to emulate some of the impacts that we might see from limiting their respiration. So at this part, what we're doing is kind of cinching down, again, simulating that feel of not being able to potentially take a full breath. We are, for this study, a little bit on the conservative side and kind of making everybody do that. And that's not necessarily true for everybody, but part of the thought is that if the findings from this study are riskier on the ground, then we may be able to have margin back that basically better protects the crew in flight. And so trying to cinch that down, trying to limit within reasonable degree the kind of fullness of a breath that someone's able to take. So next, we're going to be donning some physiologic sensors.
Bioinformatics sensors are what we look at as more of a discipline. So it includes sensors and instrumentation to collect, for instance, physiology data, in our case, crew members or astronauts, and then also how we collect that data and also visualize it. So that's kind of all-encompassing for what bioinformatics is.
We've got a number of sensors that we'll be putting on today. The first one where we're getting a lot of our data is a metabolic analyzer. And so we'll be putting on a mask. We'll be measuring everything that I'm breathing in as well as what I'm putting out, which also includes the gas blend that we're providing to the subjects as well that does have different levels of CO2 in it depending on the specific test point that we're looking at. So we're looking at things like ventilation and respiration, consumption of oxygen, production of carbon dioxide, et cetera. You'll see that we are putting on some transcutaneous CO2 monitors. So trying to understand what are the levels of CO2 in the body, how is that building up over time. We also have heart rate as a measure of physical workload, and that can also tie to CO2, and you may see some different impacts on the workload and the body's response to different levels of CO2. We also have a forehead sensor as well, looking at oxygenation in the blood as well. We don't want people to become too hypoxic during this as well because of the gas blends that we're providing. So we're constantly monitoring basically a lot of the normal vitals that you would see when you go to the hospital or something to that effect. So now that we've got all of our sensors on, we're ready to collect all of our scientific data and measures. The next thing we're going to be doing is getting into VR, into virtual reality. And so for this simulation, we're simulating a contingency walk back on the lunar surface. We're pretending that the crew member is some max distance away from safety, and they're going to have to walk along the lunar surface, generating that workload, building up the CO2 in the spacesuit effectively, and we're trying to see if they can get back. All throughout that while and every so often, we're being asked questions about how are we feeling? Do we have any symptoms like dizziness or nausea or headaches?
We'll start with a headache, 0 to 7.
Which are all well-known symptoms reported in the literature for CO2. Additionally, as we're going through VR, every so often we'll be administering a cognitive test called the digit symbol substitution test, where we kind of are looking at some different parts of cognition and trying to understand, are there any mental or cognitive impairments? Just because physically you can handle the levels of CO2 that are building up in the spacesuit, cognitively you may not be able to. And we don't want our crew members getting lost or unable to complete certain contingency or emergency steps or reacting to, say, a caution and warning system or whatever they may be doing in this case. So trying to understand what's the impact on both the physical response as well as the cognitive response of the subjects as we go through this simulated walk. So during this walk back, we are simulating this on the lunar surface. So this map is recreated from different satellite or LiDAR type data. And we've kind of recreated that map one-to-one with one of the potential landing sites that we expect to see on the moon.
It's basically we create what the buzzword is digital twin, right, of the environment. It's a math model and a simulation environment and all the correct graphics that make a virtual digital twin of whatever space systems they're training for or want to experience. So to make the user feel really immersed, you need to create the environment and for the moon, the terrain, right? The terrain and the lighting conditions as real as possible using real empirical data, right? So real data from the LRO mission, height map data, and real lighting data, all the intensity of the sun, the brightness, the lumens, the size of the sun. So create that real environment. And then add to that digital twins of any subsystem that's on the moon. The suits, you have the rovers, you might have habitats in the future, you have tools, you have a tool cart. So we have the graphics models for all that so we can recreate that. And then you drive your immersive graphics environment with data from those real digital twins. So it's real data, so things are moving correctly with the correct dynamics and the correct motion and kinematics and dynamics of that real system. So when you put all that together, either the astronaut that's in a training environment or if you're doing it for analysis, you get as close to the real world as you can get.
So at this point, I'm just now completing the hour-long simulated walk back. We've gotten all of our measures. We've gotten a lot of great data from today. And so one of the things, again, safety first that we want to do is monitor return to baseline. So let's observe the subject. Let's make sure they're able to recover from the different levels of CO2 or any of the symptoms that they might have been experiencing. We can collect more data at that time to determine what is the time to recovery. Is this really leaving more of a longer lasting impact on the subject or crew member ultimately?
What are the kinds of missions that we could use this kind of equipment with in the future? I definitely think the lunar missions, and you can see by the sand and the rocks that we have here, we're thinking very much about the moon. That's our immediate focus of this APACHE environment and VR. But we're also starting to think about Mars. And Mars is a little bit farther away, but the challenge is even greater. We're going to be very, very far from home. You are not going to have instantaneous calm with the ground. Once you burn for Mars, you're not coming back probably for 2.5 years. So there's going to be even more testing and more training.
PERSAIDS, or the Personal EVA Informatics and Decision Support System, is primarily looking at a Martian EVA operations. And so how does that look like as far as that interaction? So we have first a pre-EVA planning step that looks at what tasks they're going to be doing, where they're going to have to traverse out to be able to successfully complete an EVA. And then we look at the data components for the individual to track those consumables along the planning stage. And once we have that planned out, that's the as-planned EVA timeline that we have an IV crew member then direct the EV crew members through. And so we have the intravehicular crew member and the extravehicular crew member. So the person doing the spacewalk versus someone who's inside. And so then the EV crew member will put on the suit simulator, for instance, in VR, and we'll go through, for instance, a Martian EVA being directed for specific geology tasks or maintenance tasks from the IV crew member. So in PERSAIDS, within the APACHE environment, we end up using a few different modalities of walking around. We call it traversing in EVA. And so we use a passive treadmill, so we keep them stationary, and we can have them walk along a traverse path. We can really get a lot of good data based on speed and resistance that will track back to performance. That allows us to answer a bunch of questions. We also use an Infinideck, which is an omnidirectional treadmill. And so that gives the individual more freedom to move around, to be able to do geology in the actual space. And so to be able to walk, we have those two different modalities of walking around. We also have transitions into the sandbox where we can actually do simulated geology tasks in a hybrid reality environment. So we can go from VR to hybrid, or also stay in VR and do geology in the sandbox. We're primarily looking for performance measures of heart rate, metabolic rate for heat loading. We look at core temperature, so we actually have ingestible core temperature pills that we look at. We have skin temperature that helps us map back to a liquid cooling environment. So it's all encompassing so that we can get this performance. And so that's the whole component of Perseid. It helps that individualized decision support if, for instance, a crew member is overheating or they're getting slower in their EVA, we can make sure they get back safely by changing that timeline and assisting the automation between the two IV and EV crew members.
As we start to research the conditions of future spaceflight, virtual reality is going to play a central role because we really have to mimic these unique conditions. How do you research going to Mars? Well, you have to start mimicking the conditions you expect for Mars. We collect data in what are called analog environments, where we will actually build out physically maybe the habitat or different aspects like a sandbox behind me that we're expecting for future spaceflight and have people do research activities and training in that. But we can't do that for every possible scenario, and it's really hard to do with multiple spaceflight stressors. So virtual reality allows us to be able to mimic both the physical through what the movements they're doing with the VR on, but also the psychological aspects of things like extravehicular activity. You are now actually on Mars doing a spacewalk. And what's that like? You are now traversing 6 hours onto the Mars surface through VR. We're not going to be able to mimic that in real life. A 6-hour VR can actually do that. And so we can push the limits and really mimic what we're expecting for future spaceflight through virtual reality.
And so this is where VR becomes absolutely critical. We haven't put humans in this environment. We've never been to the South Pole of the Moon. We have not done any lunar exploration in darkness or low sun angle. And so we have some other VR assets at NASA where we can actually play with the lighting. And so you can have a computer simulation of what that lunar lighting is going to look like. And you can see how you would do these tasks in the lunar lighting. And you can evaluate, hey, is this even feasible? Should we even be trying to do this at this light angle? And so we're going to do all of that kind of testing and training here. We've got the sandbox, and you can vary the lighting conditions incredibly easy in the VR model. And so we can define the limits of what we're capable of and what the system is capable of. And then within that, we can figure out those little permutations about how we want to change the mission or our equipment or our operations in order to accommodate that. But we've got to have that. You can't do that. If you just put a bunch of lights in here, you would not replicate that environment. You have to be able to have that computer model. So that's where VR is going to be incredibly useful.
It's also important that the crew have access to and training time in partial gravity facilities in an actual pressurized spacesuit. Especially with the commercial spacesuits coming online, it'll be really important that the crew have experience on the actual lunar or Martian surface by way of virtual reality or in an actual pressurized spacesuit at partial gravity. It's really important and paramount that they have access to and training for all of these different things in order to optimize success for future EVA.
Virtual reality has a lot of potential for use here at NASA, particularly with training. So allowing the crew to experience what it will be like to be on the surface of the moon or the surface of Mars before they get there. And so we have lots of different ways that we simulate EVAs. They all have their pros and cons. And so virtual reality is a critical part of giving that full picture to the crew members before they go so that they can experience what it'll be like and allow them to kind of understand what it will be like to do an EVA on the surface.